So again, none of this information is new. This is sort of a summary or a recap of the three big type functions that we've talked about this year. So linear functions we worked on last semester. We had a unit where we looked at all their different properties, what their graphs look like, some of their key features. And then we had a unit where we worked on solving those linear equations. We also talked about exponential functions earlier this semester. And then quadratic functions, we just spent 2 units working on. So these are the 3 major types of functions that we covered in Algebra 1. What we're going to do today and tomorrow is essentially recap them, make sure we can tell the difference between them. Because in Algebra 2, you're going to start by looking at quadratic functions and their sort of larger family called polynomial functions. So all the stuff that we've worked on in these last 2 chapters is where you're going to start in Algebra 2 next year. You're also going to revisit exponential functions and dig a little deeper into their properties and some other things that we didn't focus on in here that we can also do with exponential functions. And then linear functions are also going to pop up throughout Algebra 2. So they won't be a major focus, but they'll be sort of a supporting character. You are going to talk about a few other types of functions in Algebra 2 as well, but these kind of set the foundation for that next course. So linear functions look like a line. Their graph is a straight line. The word line is right in linear. Okay, so that's how I remember that the graph looks like a line. This line has a positive slope since it's rising from left to right, but I could also have a line that has a negative slope, one that's decreasing from left to right. Okay. A linear function always looks like a straight line. No curves, no minimums or maximums, no bends. Always a straight line. If I look at a table for a linear function, as the x's are increasing by 1, what I should be able to see in the y's is that I am adding or subtracting the same amount each time. So if I look at this table, to get from -2 to -1, I would have to add 1. To get from -1 to 0, I would have to add 1. To get from 1 to 0, I would have to add 1. To get from 1 to 2, I would have to add 1. So we're adding the same number every time for those y values for a linear function. Now, in this case, it was 1. I could be adding 7 every time. I could be subtracting 4 every time, as long as I'm doing the same thing every time. That's a linear function. We had 2 different types of linear functions that we used most often. Slope-intercept form and point-slope form are the 2 forms of a linear function that we use the most. For both of these functions, that m represents our slope, and the b in slope-intercept form represents our y-intercept. If we look at point-slope form, the x1 and the y1 represent a point on the graph. So x1, y1 is a point on the graph, which is why it's called point slope form. And then we also talked about applications for linear functions. So an example of that would be like what we have over here. So a rideshare company charges a $5 reservation fee and $20 per mile. So this $5 reservation fee would be, if I were to look at a graph or talk about this in terms of a function, would be like my intercept. And then that $20 per mile would be our slope. That's how much I change by for each point. If I were to list prices in a table, every mile would be another 20 cents. So I'm increasing by 20 cents every time. So that would make this a linear function because I change by the same amount every time. The next type of function we talked about is an exponential function. So here we have an example of exponential growth. Our growth starts out slow, and then as our y or our x values get bigger, our growth really starts to take off. You see some bigger jumps here as our x values get larger. So this is exponential growth. We also talked about exponential decay. That's where our values decrease. So we start off big, and then we have large decreases at first that sort of taper off into smaller decreases. So this is growth when I go up from left to right, and this is decay when I go down from left to right. In a table, we can identify an exponential function because my y values aren't increasing or decreasing by the same amount, they're multiplied by the same number each time. So for a linear function, I'm adding or subtracting the same amount each time, but for an exponential function, we're multiplying by the same amount each time. Now that might be a little difficult to see with our fractions here, but to get from, let's say 1 to 2, we could multiply by 2. To get from 2 to 4, we'd multiply by 2. And this same rule applies to these as well. To get from a fourth to a half, we could multiply by 2. To get from a half to 1, we could multiply by 2. So for an exponential function, we're always multiplying by the same number. Now, the number that we multiply by could be a fraction. If our y values are getting smaller, that means we're multiplying by a fraction. So we're cutting that number in half every time, or we're cutting it in a third every time. Our exponential functions have this form. A is our initial amount. And then B, the base for our exponent, is our growth or decay factor. So this would be for our table what we multiply by every time. And then an example of this would be something like the bear population in a national park is originally 6 bears, but it doubles every year. So we have that initial amount, that original number of bears, and then we see how it changes each year. We double the number of bears each year. Now, because we're multiplying, as it doubles, we multiply by 2. That means we're not adding the same number of bears every time. If we start with 6 bears and we double it, that means that first year we're going to add 12 bears. And then we take that number and we double it. So the next year we're adding 24 bears. Right? Since I'm not adding the same number of bears every time, this would not be a linear function because we're multiplying instead of adding. And then finally, we again just spent 2 units talking about quadratic functions. The graph of a quadratic function is called a parabola. This is a parabola that's opening up, but I could also have a parabola that opens down. In a table, we're looking for addition and subtraction patterns, but the pattern's a little bit different than in a linear function. So if we look at our y values here, to get from 4 to 1, we would have to subtract 3. To get from 1 to 0, we would have to subtract 1. To get from 0 to 1, we would add 1. To get from 1 to 4, we would add 3. So for my y values, I am not adding and subtracting the same thing every time. In our linear functions, it was the y values that changed by the same amount every time. We don't have that here for our quadratic functions, but there is a pattern in these numbers. To get from -3 to -1, we would have to add 2. To get from -1 to +1, we have to add 2. And to get from 1 to 3, we have to add 2. So these numbers are the same. Does that make sense, this difference here? So the y's aren't changing by the same amount every time, but there is a pattern in how they change. That's how I identify a quadratic function from a table. We had 3 different types of quadratic functions that we looked at, 3 different versions of quadratic functions. We talked about standard form. For standard form, that c value gives us our y-intercept. We also had vertex form, and for vertex form, h comma k identified our vertex. And then we also had intercept or factored form. And for this form, m and n were our x-intercepts. And then we talked about just the other week how a lot of the application problems that we see for quadratic functions are about projectiles, and that's what we have here. A rock is thrown upwards from a 200-foot tall cliff with an initial velocity of 96 feet per second. So that rock is going up, and then it's going to come back down. So that's a parabola. That's a quadratic problem. So there we have a quick refresher of the 3 major function types that we've talked about. What we're going to look at next is being able to differentiate between these different functions when I have a context, when we have a table, when we have a graph, and then eventually when we have a function. So on the next page, what we're going to do is take a look at some problems in context, some applications, some graphs, and some tables, and determine if these are linear, exponential, or quadratic functions. So for A, it says the temperature of a mug of hot coffee reduces by 1/4 every 10 minutes. Now, if this were telling me the temperature reduces by 4 degrees every 10 minutes, that means I would change the temperature by the same amount every interval of time. But I'm not saying it reduces by 4 degrees. I'm saying it reduces by 1/4. So I would take whatever the current temperature is and take away 1/4 of those degrees. It would reduce by 1/4. And then for that new temperature, I would find 1/4 of that and subtract it. And then for the new temperature, I'd find 1/4 of that and subtract it. So this 1/4 is going to change every time. It's going to be a little different every time. That means that this is an exponential function. For B, a plumber charges $50 per hour. So for the first hour, it's $50. For the second hour, it's another $50. For the third hour, it's another $50. Every hour, we always add on the same amount. That makes this a linear function. And then you had a problem like C in your review for Unit 9. You dive to the bottom of the pool and then return to the surface. So let's say this is our water line. You go down and you come back up. That's a quadratic function. Questions for me so far? Okay, let's take a look at the graphs here. D, what type of function is that? What? Linear, yeah. Looks like a line, so it's linear. Remember, linear has the word line right in it. How about E? Exponential. And then F, quadratic. And now let's look at our tables. Remember, we're focusing on how those Y values change. I tend to start a table by looking at, can I add or subtract the same thing each time? We started with linear functions back in the fall. That was the first type of function that we talked about. So that's why I start by looking to see if it's a linear function. If you want to check if you can multiply by the same thing first, that's fine too. I'm going to start by looking to see, can I add or subtract the same thing? So for H, remember I'm focusing on those Y values. To get from 11 to 8, we would have to subtract 3. To get from 8 to 5, I would have to subtract 3. To get from 5 to 2, I have to subtract 3. To get from 2 to -1, I have to subtract 3. Since I'm subtracting the same number every time, that means that this is a linear function. Adding or subtracting the same number every time gives you a linear function. Let's take a look at I. I'm going to start the same way. What am I adding or subtracting from these Y values? So to get from -1 to -2, I would have to subtract 1. To get from -2 to -1, I would be adding 1. From -1 to 2, that means I'm adding 3. And from 2 to 7, I'm adding 5. So this is not a linear function because all of these numbers are different. So the next thing I want to check is there a pattern in these numbers? Yeah, I'm adding 2. To get from -1 to +1, I have to add 2. To get from 1 to 3, I add 2. To get from 3 to 5, I add 2. So since this second row is the same, that means this is a quadratic function. And then finally, let's take a look at J. So again, I'm going to start the same way. Am I adding or subtracting the same thing each time? So to get from 1 to 2, I would have to add 1. To get from 2 to 4, I have to add 2. To get, bless you, from 4 to 8, I have to add 4. To get from 8 to 16, I have to add 8. So it's not a linear function. Let's check quadratic. To get from 1 to 2, I add 1. To get from 2 to 4, I add 2. To get from 4 to 8, I add 4. This second row is not the same, so it's not quadratic either. So it's not linear, it's not quadratic. The last option I have is, can I multiply by the same number each time? So to get from 1 to 2, I could multiply by 2. That would work. To get from 2 to 4, I could multiply by 2. To get from 4 to 8, I could multiply by 2. And to get from 8 to 16, I could again multiply by 2. If I can multiply by the same number each time, that would make this an exponential function. Questions for me? Okay, so this is a short recap again of those 3 major types of functions that we talked about. On the next page, there's some practice problems where I'm asking you the same thing. Classify each of these as linear, exponential, or quadratic. So you've got a couple of applications there, you've got some graphs, you've got some tables, and then you've got some function examples, okay? Tomorrow, we're going to be on Zoom just for the first couple minutes of class. So I can give you directions and give you the information you need to get onto that Desmos activity. And that activity is going to ask you to do the same thing that I'm asking you to do here. So it's going to give you graphs and tables and functions, and it's going to ask you to sort them into, these are exponential, these are linear, these are quadratic. It's going to ask you to categorize, okay? So this is to set you up for success for tomorrow, to do a little practice.